At 828 meters, the Burj Khalifa forces a confrontation with the limits of physics. You cannot build a structure of this magnitude by scaling up. Past a certain height, standard engineering models break down nonlinearly. If you take traditional end-bearing foundations, a symmetric building profile, and standard concrete pumping methods, and simply make them larger, the structure will fail long before it reaches the peak. Crossing into the mega-tall category requires overcoming three physical thresholds. First, the geotechnical challenge. Loose desert sand lacks bearing capacity for massive loads. Second, the aerodynamic threat. High-velocity winds risk harmonic oscillation. Finally, material transport. Pumping concrete straight up risks rupturing pipelines. To push past the 800-meter mark, engineers had to abandon the strategy of brute force stiffening. Instead, they designed a highly reactive, integrated physical system. The first problem begins underground. When engineers drilled exploratory boreholes to depths of 140 meters, they found no bedrock capable of carrying the building's extreme load. They found only loose sand and gravel. Standard end-bearing piles transfer a building's weight directly downward into a hard subterranean rock layer. Without that solid rock base, a traditional pile simply pushes through the loose soil and continues to sink. The solution relies entirely on surface friction. Rather than relying on a hard surface below, a friction pile utilizes the soil surrounding it. As vertical force pushes down on the pile, that load is diverted horizontally into the adjacent sand. The deeper the pile goes, the tighter the surrounding soil grips it, resisting downward movement. To support the mass of the Burj Khalifa, engineers bored 194 of these friction piles into the ground. Each one is 1.5 meters in diameter and stretches approximately 43 meters long. Drilling holes of this size into loose sand normally results in the walls collapsing inward. To prevent this, excavation teams pumped polymer slurry into the boreholes as they dug, using the liquid's hydrostatic pressure to hold the sand walls in place until the concrete could be poured. Over these 194 piles sits a 3.7-meter thick raft of self-consolidating concrete. This solid base collects the total weight of the structure and distributes it evenly across the entire pile matrix. The result is that a 500,000-ton structure does not rest on the earth. It effectively floats within it, suspended by the aggregate friction of millions of individual sand grains. Securing the tower against gravity was only half the subterranean problem. The local groundwater is highly aggressive, containing up to 4.5% salt and 0.6% sulfates. If chlorides from this saline groundwater penetrate the concrete, they initiate an oxidation reaction on the internal steel rebar. Over time, the steel corrodes, weakening the foundation from the inside out. Relying on the physical barrier of the concrete alone is a passive defense. Given the chemical concentration in the soil, the mathematics showed that passive protection would eventually fail over the lifespan of the structure. Engineers required an active defense, an impressed current cathodic protection system. The system works by burying a sacrificial titanium anode mesh in the foundation. A continuous, low-voltage positive DC connection is applied to this mesh, while the structural steel rebar is connected to the negative terminal. This electrical circuit forces the structural steel rebar to act as a cathode. It floods the steel with electrons, completely neutralizing the oxidation reaction and shifting the corrosion process entirely onto the replaceable titanium mesh. The physical stability of the Burj Khalifa depends on a continuous electrical heartbeat. If that DC power supply ever fails, the foundation immediately begins to chemically dissolve. High above the ground, the engineering priorities shift. Approaching 800 meters, raw wind pressure is secondary to a more complex threat: harmonic oscillation. When wind flows around a uniform shape, it creates alternating low-pressure zones in its wake. This produces rotating air currents, a phenomenon known as vortex shedding. If the frequency of these alternating vortices approaches the natural frequency of the building, it induces violent escalating lateral movement that can tear the structure apart. To counter this, engineers anchored the structure around a hexagonal core, buttressed by three structural wings arranged in a Y-shaped footprint. During the design process, the engineers optimized this layout by rotating the entire building 120 degrees, aligning the structure to directly brace against the region's prevailing winds. As the tower ascends, these three wings step back at irregular shifting intervals, creating a progressively changing, spiraling vertical profile. These irregular setbacks actively disrupt vortex shedding. By presenting the wind with a continuously changing cross-section at every height, the building prevents alternating pressure zones from organizing into a regular pattern. The Burj Khalifa does not survive high-altitude winds through rigid stiffness. It survives by aerodynamically dismantling the air currents before they can combine into a destructive force. Building this aerodynamic shape required an immense logistical operation, delivering high-performance 80 megapascal concrete in a single vertical lift to a height of 601 meters. Moving concrete to that height forces the heavy-duty Putzmeister pumps to operate against a static pressure head of roughly 150 bar. Inside a 150-millimeter pipeline, concrete moves via plug flow. A central core of solid aggregate glides upward, suspended by a microscopic lubricating layer of cement paste right at the steel pipe wall. Under extreme vertical pressure, this thin paste layer can be squeezed out. When that happens, the aggregates interlock, friction spikes, and the pipe suffers a catastrophic blockage. This chart plots the pressure changes over vertical height for the different concrete mixtures during the pumping trials. By testing different formulas horizontally, engineers found a way to manipulate the rheology and lower the friction factor. The critical variable was aggregate size. Reducing the maximum aggregate diameter from 20 millimeters down to 14 millimeters increased the overall paste volume, which dropped the required pumping pressure by a crucial 15%. Even with the pressure solved, the concrete faced a 40-minute vertical transit inside hot steel pipes in a 50-degree-Celsius desert. The risk of the concrete curing mid-pump was high. The thermal solution was to replace the mixture's water content entirely with flake ice. This maintained a strict maximum placement temperature of 33 degrees Celsius, slowing the hydration process until the concrete reached its final elevation. Crossing this final vertical threshold required treating concrete not as a solid building block, but engineering it as a highly calibrated, temperature-controlled, non-Newtonian fluid. When you examine the mechanics required to build it, the Burj Khalifa stops looking like a static architectural monument and reveals itself as an active, integrated machine. It manages 500,000 tons of vertical mass by redirecting it into radial sand friction. It utilizes a continuous feed of direct electrical current to halt the molecular degradation of its own foundation. It deploys a spiraling, asymmetric geometry to scramble atmospheric fluid dynamics before they can take hold. And it achieves extreme verticality by balancing hydraulic pressure and thermodynamics, down to the millimeter of the aggregate and the precise temperature of the water. All of these overlapping systems work simultaneously, holding the tower in a precise state of equilibrium against gravity, chemistry, and the wind. The 800-meter threshold could never be crossed by holding on to traditional structural assumptions. It demanded the design of a living, actively defensive engineering system.